just like we can classify species, we can also classify ODEs. So here's some lingo that we'll use. First of all, there's the order of a differential equation. It's the order of a ODE. And all this is, it's the highest derivative that appears. This will be explained with some very quick examples. So highest derivative that appears. So for instance, y prime is 2y plus 1. That is a first order differential equation because only the first derivative of y appears. It's a first order ODE. But for instance, if you take y double prime minus 5y prime plus 6y equals 0, because the second derivative appears here, we call this a second order differential equation. Or OD. That's one thing. And now, aside from that, let's now go from the easiest scenario to the hardest scenario. So the most basic classification is what's called a constant coefficient differential equation. Coefficient, ODE. And it's literally what it says, namely that the coefficients are constants. Coefficients are constants. Now, for general order ODE, we can write it down, but it's easier just to do it for second order ODE. So second order constant coefficients, so CC ODEs, they're ODEs simply of the form A y double prime plus B y prime plus CY equals maybe some function of t on the right hand side. So the whole point is the coefficients A, B, and C in front of y and its derivatives, they're constant. So once again, here are a couple of examples. For instance, y double prime minus 5y prime plus 6y is e to the 2t. Once again, the coefficients in front of the derivatives, they're constants, so this is constant coefficient. Even though there's an e to the 2t on the right-hand side, that would be still okay. But on the other hand, if you take t squared y double prime plus 2y prime plus 3y equals 0, because the coefficient in front of y double prime depends on t, this is not constant coefficient. Not constant coefficient. Now, you may ask, what if the coefficients depend on t? This is what's called a linear differential equation. So it's kind of next step. Linear ODE. So here, the coefficients depend on t. It's a ODE. Depend on t. On t. So once again, a second order linear differential equation. Linear ODE. It would have the form A of t y double prime plus B of t y prime plus C of ty equals f of t. Okay. So same thing as before, except this time the coefficients in front of y prime, y double prime, and y depend on t. So for instance, a couple of examples. If you take a t squared, y double prime plus sine of t, y prime plus 2y equals 0, since the coefficients in front of our functions, y double prime, y prime, and y, since they depend on t, those are linear ODEs. And you may ask, what is an example of a nonlinear ODE when, for example, there are things like squares? Like if you take y double prime squared plus sine of y prime plus, I don't know, 3y equals e to the t. This is not linear because it's not of the form a function of t times y double prime plus a function of t times y prime plus a function of t times y equals f of t. Here, you really have everything jumbled together, where you have, let's say, y double prime times y double prime. That would not be okay. So this is not linear. Last but not least, an example that confuses a lot of students. If you take y double prime minus 5y prime plus 6y equals 0, this is still linear. Linear because simply in this case, the coefficients, they're constant functions of t. So going back to this thing, a of t would be 1, b of t would be minus 5, c of t would be 6. It's still a function of t in the calculus sense. And by the way, in case you're wondering where this terminology comes from, well, it comes from linear algebra. Why is it called linear? Because if you take the transformation t of y equals y double prime minus 5y prime plus 6y, this is a linear transformation. Transformation, which you may have learned from linear algebra. If this doesn't make any sense to you, don't worry. We'll not really mention this any further. Okay. Now, once again, we have those linear differential equations, but also a bit of nonlinear ones. Now, for linear ODE, there is a subspecies that is very important. It's called homogeneous. ODE. Again, that's for linear. ODE. And it's simply homogeneous when the right-hand side is 0 and inhomogeneous if it's not. If f of t is 0 and inhomogeneous, homogeneous. If f of t is not. And again, it's much easier to explain with an example. For instance, take the following linear ODE, t squared y double prime plus sine of t y prime plus 2y if the right-hand side is 0, this is homogeneous. But if you take the same equation and you change it to something non-zero, t squared y double prime plus sine of t y prime plus 2y, let's say is t squared, that makes it inhomogeneous. And the cool thing is, we will see it later, we can use homogeneous ODE to solve inhomogeneous ones. Very mysterious, but you'll see it'll make much more sense. Now, once again, there was the world of linear ODE, and then there are the nonlinear ones, which is literally everything else. Linear ODE. Everything else. And the important thing to understand, nonlinear ODE, they're crazy hard, but also crazy interesting. And in fact, I want to give you 3 really cool applications of this, because take the following, which is a bit out of this world. So take y prime, okay, not too bad, divided by square root of 1 plus y prime squared. Ooh. And not only that, take this whole monster, differentiate it, and set it equal to 0. And you may ask, who in the world would come up with this? Well, let me ask you, do you wash your hands? Because in fact, this is what's called the minimal surface equation. That's ODE, and it models the behavior of soap films. Soap films. So if you want to know how a soap bottle behaves, it behaves according to this differential equation. This is a little bit too hard to study. We'll not do it in this course, but one equation that we will study is simply y prime equals 2y times 1 minus y over 3, which is a nonlinear ODE because of the square term. So say 2y minus 2/3 y squared. So it is nonlinear. And that we will solve explicitly. It's called the logistic equation. And it models population growth. Because we did cover the bacteria model. Now it turns out this has some limitations, and we'll see that the logistic equation is a better model for this. Last but not least, there's an important equation in physics called the pendulum equation, which can be written as follows. So the second derivative of an angle plus g over L, so gravitational constant over length, sine of theta equals 0, and that's called the pendulum equation. And what it does, it models a pendulum of length L. Or more precisely, it models the angle of pendulum of length L. So in other words, the way to picture this is the base. It's all about the base. We have a very nice pendulum here that just swings back and forth. Pendulum. And of length L. And because it swings back and forth, it does make an angle with the vertical line. This angle, and it turns out our differential equation models that angle. Now, it is so hard that it has no explicit solution. So there's no formula for the solution of this equation. But the cool thing is we can approximate it with an equation that does have a solution. Because if you use the infamous approximation, sine of theta is roughly theta. Sine of theta is roughly theta for theta small. Then that ODE turns into a linear ODE. Or ODE becomes, so second derivative of theta plus G over L times theta equals 0. Equals 0, which in turn becomes a linear ODE. Because here the coefficient is 1, here the coefficient is a constant, and then equals 0. So in fact, we get a linear, in fact, even a constant coefficient ODE. And the idea is hopefully by solving this thing, we can actually solve, at least get some info for our original equation. And what I've shown you here, the process of replacing a nonlinear ODE by a linear one, this is sometimes called linearization. Which, by the way, you have done in calculus before, where you replace your function by a tangent line. It's the same. And so last but not least, I just want to show you a little picture of the ODEs we've discussed. So what we had our linear ODE, our nonlinear ones. And within the linear ODE, they're the constant coefficient.